Hello class, let me discuss to you the topic hydrostatics. Because engineers use pressure in the solution of nearly all fluid mechanics problems. In this lecture video, it introduces the fundamental ideas about pressure. So what is pressure? Pressure is the ratio of normal force to area at a point. So if we are talking about solid mechanics, if we have an area here where there is an applied force perpendicular to that area, so that equivalent force per unit area is your pressure. Or we have this formula where pressure is equals to the magnitude of the normal force per divided by the unit area. The same applies with fluids. So what's the definition of hydrostatic pressure? Hydrostatic pressure is the pressure that is exerted by a fluid at equilibrium or fluid which is at rest at a given point within the fluid due to the force of gravity. So here are the other principles that we need to consider in hydrostatic pressure. First one is the hydrostatic pressure increases in proportion to its depth measured from the surface. Hydrostatic pressure acts equally in all directions, and hydrostatic pressure acts at right angle at any surface in contact with. Let's say we have here a cubical tank. So if this is the water surface at the top, um, said there that the pressure increases in proportion to depth. So it means the deeper it goes, the higher the pressure at each point within the tank. On the other hand, we have the hydrostatic pressure acts equally in all directions, and that pressure acts at right angle to any surface in contact with the fluid. So our container is a cubical tank. So the sides in which the faces of the cubicle of the cube that are in contact with the fluid are these faces, including the bottom part of this cube. So it said there that the pressure acts equally in all directions. That's with respect to the depth of fluid. Let's say considering this level, it means at this elevation, all the pressures are equal. Not only that, the pressure acts at right angle to that surface that is in contact or perpendicular to that face. So they are of equal pressure. So the pressure here is just equal on the other side of the cube. So in support of these definitions, we have Pascal's law. Pascal's law, it is developed by French mathematician Blaise Pascal, states that any force applied to a confined fluid is transmitted uniformly in all directions throughout the fluid regardless of the shape of the container. So as you can see here on the figure, it is said that the pressure is independent of the shape and size of the container. We have here different shapes and sizes of container. Given that they are of the same depth, their equivalent pressures at the same depth are the same. So let's say at this point, the bottom of each container, given that they have the same depth, their equivalent pressures at these points, they are the same. So what is an absolute pressure, gauge pressure, and vacuum pressure? Let's start first with vacuum. A vacuum is a space that has all matter removed from it. The very example for that is the outer space, where there's no atmosphere, there's no air, there's no gas present on that space. So generally, it means that there's no pressure present in a vacuum unless there is an external or there is a source of pressure that is within the space or within the vacuum. That's when we will compute the vacuum pressure. So if there is an external source of pressure that is within that vacuum. For the absolute pressure, it is a pressure that is relative to the zero pressure in the empty air-free space of the universe. This reference pressure is ideal or absolute. So it means that we have a reference pressure of zero in a vacuum. So it means if our pressure reading here in a vacuum in the outer space is zero, so when we try to bring this soccer ball in the outer space and we take the reading or we determine the pressure inside that ball, so the pressure reading inside that ball will be your absolute value. So any pressure that is measured in a vacuum or in the empty air free space of the universe, so that's your absolute pressure, where our reference pressure in the vacuum is zero. So for the gauge pressure, we also call that as relative pressure. These are pressures above or below the atmosphere and can be measured by pressure gauges or manometers. Difference between an absolute pressure and the prevailing atmospheric pressure is your gauge pressure. So our gauge pressures, they are designed to exclude or to subtract the atmospheric pressure in their reading. So when you try to remove this, it will automatically have a gauge reading of zero. So what is an atmospheric pressure? Atmospheric pressure is the pressure at any point on the Earth's surface from the weight of the air above it. So the device that we can use in measuring the atmospheric pressure is a barometer. So the atmospheric pressure decreases as the altitude increases. So the higher the elevation, the the lower the pressure is. The lower the elevation, the higher the pressure. So a barometer uses mercury in measuring the atmospheric pressure. So this is what it looks like. Next, these are the solutions in determining the gauge pressure, such as the difference of absolute pressure and atmospheric pressure. The vacuum pressure is equals to atmospheric pressure subtracted by the absolute pressure. Another solution for vacuum pressure, it is also equals to negative gauge pressure. So come now to variations in pressure. To determine the change in pressure between 2 points in a fluid, so we have delta P is equals to the product of the unit weight of the fluid and the difference in elevation h. It's just the product of unit weight of the fluid and the difference in elevation between the 2 points. So we can rewrite that as P2, or the pressure at point number 2, minus pressure at point number 1 equals to the product of unit weight of fluid times h. So let's say we have a given pressure at point 1. If we are to determine the pressure at point 2, we can rewrite that as pressure 1 Then we will add the unit weight of the fluid times the H. By the way, most of our calculations here is we use gauge pressure in determining the pressures here in our sample problems here in this lecture. So actually most of the problems that we will encounter in fluid mechanics and hydraulics is that we use gauge pressure. So that's how we compute the difference in pressure or the pressure at any point within the fluid or within the liquid. So let's say that point 1 lie in the free liquid surface. So we know that the gauge pressure, when we measure the, the pressure in the air, it automatically remove the pressure measurement due to atmospheric pressure, and it will automatically read have a gauge reading of 0. So therefore, if we will start at the liquid surface where the pressure there is 0 from the previous equation that we have, which is P2 equals to P1 plus gamma H, um, we can already determine the pressure at the second point, which is equals to unit weight of the fluid times H. So we can easily determine the pressure at any point below the liquid surface given the difference in elevation and its unit weight. So at any depth, we can determine the equivalent pressure with reference to the liquid surface. Okay, but if we have a given pressure at point 1, so we use that pressure there. But if we will start the liquid surface using the gauge pressure reading, that is 0. On the other hand, if we have points 1 and point 2 lie on the same elevation, let's say here is point 1, they are of the same elevation, it means that there is no difference in elevation between the two. So H is 0, this will be cancelled out. Therefore, pressure 2 is equals to pressure 1. So it means that, again, if point 1 is of the same elevation as point 2, therefore the pressure present at point 1 and point 2 are the same. So at any point within the same elevation as point 2, they are the same in pressure, measured from the liquid surface. So for pressure below layers of different liquids, so for example, we have a closed tank here with 3 layers of liquid. And we also have a pressure present at the top, an air pressure. So if we were to determine the pressure at the bottom, here's the corresponding solution. The pressure at the bottom is equals to the sum of the products of the unit weight and its corresponding height. So unit weight of liquid A times H1, unit weight of liquid B times H2, and unit weight of liquid C times H3. We can rewrite that as this one. And just add the air pressure at the top. So pressure at the bottom is just the sum of the product of the unit weight of the liquid and its corresponding height plus the air pressure. So if we are going to determine the pressure at this point, say at this point, so from the top, we'll just include pressure, air pressure, then the sum of the products of unit weight of A and its corresponding height. So it means, let's say this is point B. So if we want to determine the pressure at point B, so just add the air pressure. So from the top, plus, since air pressure is already any unit of pressure, you can just simply write that. And for liquid A, unit weight of A, or unit weight 1 times H1 plus unit weight known B and H2. So that's how you determine the pressure at the. So let's have some sample problems. What is the pressure 25 meters below the ocean? Use specific gravity of salt water 1.03. Say this is the free water surface of the ocean and we are required to determine the pressure 25 meters below. So given specific gravity of seawater is 1.03. So to determine the unit weight of the salt water, uh, to determine the unit weight of any fluid with given specific gravity, just multiply the unit weight of water to the specific gravity. So the standard unit weight of water at 4 degrees Celsius is 9.81 kilonewtons per cubic meters. So the specific gravity is 1.03. The unit weight of salt water is equals to 9.81 times 1.03. That's 10.1043 kilonewtons per cubic meters. So from our discussions earlier, that uh, if we measure the pressure from the free water surface, we can easily use this solution because the pressure at the free water surface using gauge pressure is 0. So we can easily compute the pressure at any depth, which is unit weight of water or unit weight of the fluid multiplied by H. So this is salt water. So just substitute 10.1043 kilonewtons per cubic meter multiplied by H, which is 25 meters. Cancel out meter, it remains square meter. Kilonewtons per square meter is kilopascal. So multiply this by 25. We have a pressure of 252.6075 kilopascal. This is the answer. That's the pressure 25 meters below the ocean. Next, okay. If the pressure 25 meters below a liquid is 354.68 kilopascal, determine its unit weight, mass density, and specific gravity of the liquid. So here, what's given are the pressure, which is 354.68, the depth below the liquid surface is 25 meters. So it means from the free water surface to 25-meter depth, we have a pressure of 354.68. Determine the unit weight first. So we can use again the solution. The pressure is equals to unit weight times the H. So we don't know what type of liquid is this. So the unit weight of the liquid is say gamma L. So divide both sides by H to eliminate H here. Therefore, we can rewrite the solution as the unit weight of the liquid is pressure over H. So substitute now the given 354.68 kilopascal is kilonewtons per square meter divided by H, which is 25 meter. So the unit weight of the liquid is 354.68 divided by 25. That's 14.18 0.72 kilonewtons per cubic meter. That's the answer for the unit weight of the liquid. For the mass density, to convert unit weight to mass density, uh, the mass density of the liquid is just the quotient, or you divide the unit weight of the liquid by the acceleration to gravity. So we have 14.1872 kilonewtons per cubic meter divided by 9.81 meter per second squared. So let's make our units here consistent. So we convert kilonewton to newton. Okay, convert that to newton. Just multiply 1000. So let's continue our solution here. So the mass density of the fluid is, multiplying this by 1000 for kilonewton to become newton, we will have 14187.2 newtons per cubic meters divided by 9.81 meter per second square. So just to recall, class, newton is equivalent to kilogram meter per second squared. So if we divide these two, meter per second squared will be cancelled out with the unit of our denominator, which is the acceleration due to gravity. So what remains is the kilogram and per cubic meter. So we divide now. 14187.2 divided by 9.81, that's 1446.198 kilograms per cubic meters. That's the answer for the mass density. The last question is the specific gravity of the liquid. For the specific gravity, we can use the ratio of the mass density of the liquid over mass density of water, or we can use that's unit weight of liquid divided by unit weight of water, or we can use the mass density of liquid over mass density of water. So we can use either of the two as long as we know the unit weight of water or the unit weight of, or the mass density of the water. So let's say I will use mass density of water to find the specific gravity. So the specific gravity, the mass density of the liquid is 1446.198 kilograms per cubic meter. So the mass density of water is 1000 kilograms per cubic meter. So when I divide that, we have 1.446. 1.446, that's your specific gravity. Or I can use also the unit weight of the liquid. Unit weight of the liquid is 14.1872 kilonewtons per cubic meter divided by the unit weight of water, which is 9.81 kilonewtons per cubic meter. So when I use that, we have 14.1872 divided by 9.81. Same answer, 1.446. That's your specific gravity. So that's how you solve this problem. Next, a pressure gauge 8 meters above the bottom of the tank containing a liquid reads 100 kilopascal. Another gauge height 6 meters above the bottom of the tank reads 113 kilopascal. Determine the specific weight of the liquid. Specific weight, or the unit weight of the liquid. So let's solve. Let's say this is your tank. It said there that a pressure gauge 8 meters above the bottom. From the bottom, we measure 8 meters. So let's say this is your 8 meters. Okay. We put a manometer here, and the gauge reading is 100 kilo Pascal. Another gauge height 6 meters. So lower, let's say this is your 6-meter distance from the bottom. We have a gauge reading of 113 kilo Pascal. So that's the gauge reading here. Determine the specific weight of the liquid. What is the specific weight of the liquid? So going back to our general solution in determining the change in pressure, delta P, that is equals to the product of unit weight of the fluid times H. So change in pressure, so this is 0.1, this is 0.2. So we have P2 minus P1 equals to unit weight of the fluid, okay, times H. So what is H here? That's the difference in elevation between the 2 points. So how to find H? H is just equals to, given the distances from the bottom, the gauge reading distance from the bottom of the tank, which is 8 meters for the first gauge reading, and for the second we have 6 meters. So the difference of the two height, that will be your difference in elevation between the two points. So we have 2 meters for each. So this is 2 meters. So the pressure at point 1, that is 8 meters above the bottom of the tank, that's 100 kilopascal. And the pressure at point 2, which is 6 meters above the bottom of the tank, that's 113 kilopascal. So these are given. So we can now substitute these values in our solution. So to find gamma, we divide both sides by h to eliminate h here on the right hand side of our equation, so that the unit weight will be isolated. So P2 minus P1 over h, that's your unit weight. Or we can rewrite that as the unit weight is P2 minus P1 over h. So substitute now all the given. We have 113 kilopascal minus 100 kilopascal divided by 2 meters. So again, kilopascal is in kilonewtons per square meter. Kilonewtons per square meter divided by unit in meter, that is equivalent to the unit weight, which is kilonewton per cubic meter. So we now solve this solution. We directly solve that. 113 minus 100 over 2. That's 6.5. Means we have 6.5 kilonewton per cubic meter unit weight of liquid inside the tank. Okay, that's the answer. Next, an open tank contains 5.8 meters of water covered with 3.2 meters of oil with a unit weight of 8.5 kilonewtons per meter. Find the pressure at the interface at the bottom of the tank. So we are required to determine the pressure at the bottom. So there are no given air pressure on the top portion of the tank, so it means we don't have an additional air pressure here. So we have two layers of liquid. We have water, which is 9.81 kilonewtons per cubic meter unit weight. So it means if the unit weight of water, which is 9.81 kilonewtons per cubic meter, unit weight that is heavier than the oil. So the distance 5.8 meters is from the bottom of the tank, measured from the bottom of the tank. So 5.8 meters. Then covered with 3.2 oil, so that is a lighter liquid, so it will float above the water, which is 3.2 meters. So that's your, this is oil, this is water. So the unit weight of oil is 8.5 kilonewtons per cubic meter. So compute the pressure at the bottom. So the pressure at the bottom is just the sum of the product of the unit weight of the fluid multiplied by its corresponding height. So if we have air pressure above those liquids, we can add that. But there are no given air pressure here, so it means we have zero air pressure above those liquids. So we can simply compute this by adding the product of the unit weight of oil times 3.2 meters plus the unit weight of water multiplied by the height 5.8 meters. So the pressure at the bottom is, substitute unit weight of oil, 8.5 kilonewtons per cubic meter times 3.2 meters to be added by 9.81 kilonewtons per cubic meter times 5.8 meters. So the pressure at the bottom is equals to 8.5 times 3.2 plus 9.81 times 5.8. So the pressure at the bottom is 84.098. That's in kilopascal per kilonewtons per square meter. That's the answer.